My name is Muriel.
I'm Air.
I'm Kim.
We're back now with linear programming using Simplex Method.
Today, we'll be discussing linear programming using Simplex Method. What is Simplex Method? Simplex Method is used for calculating the optimal solution to the linear programming problem. In other words, the simplex algorithm is an iterative procedure carried systematically to determine the optimal solution from the set of feasible solutions. It has more than two variables and thus too large for the simple graphical procedure. Examines the corner points in a systematic fashion using algebraic concepts. Following the two conditions need to be met before applying the simplex method. First, the right-hand side of each constraint inequality should be non-negative. In case any linear programming problem has a negative resource value, then it should be converted into positive value by multiplying both the sides of constraint inequality by -1. Second, the decision variables in the linear programming problem should be non-negative. There are 5 steps in solving simplex method. First, determine which variable to enter into the solution mix. Variable entering the solution has the largest positive Cj minus Dj. One way of doing this is by identifying the column, and hence the variable, with the largest positive number in the Cj minus Dj row of the preceding tableau. This means that we will now be producing sum of the product, contributing the greatest additional profit per unit. The column identified in this step is called the pivot column. Second, determine which variable to replace. Because we have chosen a new variable to enter the solution mix, we must decide which basic variable currently in the solution will have to leave to make room for it. Step 2 is accomplished by dividing each amount in the quantity column by the corresponding number in the selected in step 1. The row with the smallest non-negative number calculated in this fashion will be replaced in the next tableau. This smallest number, by the way, gives the maximum number of units of the variable that may be replaced in the solution. This row is often referred to as the pivot row. The number of the intersection of the pivot row and pivot column is referred to as pivot number. Third, compute the new values for the pivot row. To do this, we simply divide every number in the row by the pivot number. Fourth, compute the new values for each remaining row. All remaining row or rows are calculated as follows. New row numbers equals numbers in old row minus number above or below pivot number times corresponding number in the new row. That is the row replaced in step 3. Lastly, compute the Zj and Cj minus Zj rows as demonstrated in the initial tableau. If all numbers in the Cj minus Zj row are 0 or negative, an optimal solution has been reached. If this is not the case, return to step 1.
Maximize z, x1 plus 5x2, subject to 5x1 plus 5x2 greater than or equal to 25, 2x1 plus 4x2 less than or equal to 16, x1 less than 5, and non-negative constraints. Now we convert the constraints to equations. We add slack variables represented by s to each less than or equal to constraint. The second and third constraint will now become surplus variables, also called negative slack, can be represented as negative s, are subtracted to each greater than or equal to constraint. Artificial variables are added in each greater than or equal to constraint. It is used to resolve the negative surplus. Thus, the first constraint now looks like this. If no variable appears in an equation, then add with a coefficient of 0. This means they have no effect or influence on equations they are inserted in, but allows us to keep tabs on all variables at all times. Now the objective function will become We can now construct the initial simplex tableau. Solution mix are simply the variables. Cj are the coefficient of the objective function. In the solution mix column, add slack variables and artificial variables and add its corresponding values to the Cj column. Add the coefficients of the first constraint in the first row, the second constraint in the second row, and the third constraint in the third row. To solve for Zj value along x1 column, multiply negative m times 5 and then add the product of 0 and 2 and then add the product of 0 and 1. To solve for Cj minus Zj along x1 column, do the same for the other columns. By negative 5m, the result will become 5m plus 1. Do the same for the other columns. Optimality condition for a maximization problem. Check if all Cj minus Zj values are either negative or 0 values. If not, make another tableau. To find the new values for the second simplex tableau or iteration 1, find the pivot number. It is the intersection point of the pivot row and pivot column. To find the pivot column, along the Cj minus Zj row, find the maximum value. The column with maximum value is called the pivot column. To find the pivot row, divide the quantity value with the number in the pivot column. The row with a quotient with a minimal value is called the pivot row. The new values along the pivot row are simply divided by the pivot number. The quotient is the new value. In a non-pivot row, a formula is given to find the new values. The solution mix in the pivot column will now replace the solution mix in the pivot row. Solve for the values Zj and Cj minus Zj. Optimality conditions. Check the Cj minus Zj row. If the values are not optimal, less than or equal to the new values for the next tableau. If not, make another tableau. If you do not understand and would like to review, please play back the video.
And that's all for today. We hope we help you with our discussion.
Tune in next time for more lessons on operations research.
This is Mac. See you next time.
Bye!